Didn't I didn't think so. Okay, so what we're going to do is understand that notation first of all. If we have, let a of x be our polynomial, and it goes up to a and x to the n, and b of x is going to go up to x to the s, so they're going to be different lengths, not necessarily the same length. We want to calculate a of x times b of x. And I really want to do this using a scratch piece of paper. And we'll get this flipped back around in a minute, but I'll write on it. Set theory and logic too.
Oh, yeah, we can do it.
And statistics, yes. And I did power statistics for most of statistics, but yeah.
Well, I took stats.
Oh, I should unplug it from the screen. Okay, so we had, let's go back up to the top. We had a of x is going to be a0, a1x up to an x to the n. B of x is going to be 0, bs x to the s. And so we want to multiply these two together. When you're multiplying polynomials together, we did FOIL on it, remember? Sort of. But in this case, we have more than 3 terms each. What the book is going to do is going to say, okay, suppose, maybe I should write that first. Suppose they don't have the same number of terms, then we can put in zeros to fill out the same number of terms. So if n, suppose n is bigger than s, then we're going to prepend onto the end of it, b of x will be b0, b1x, up to bs x to the s plus 0, x to the s plus 1, and just put zeros onto the end so that you can take it up to x to the n, so it has the same number of elements. They do that for the notation, to be able to make the notation easy. So that's the first thing that they do, is they put those zeros on there. And then they just say, well, we'll just call them these values b sub s plus 1 up to b sub n, just saying that those ones are 0 if necessary. So then they just rewrite this as b0, b1x, all the way up to b sub n x to the n. So that's where that comes from. They don't have to be the same length, but you can add 0 terms to the end of it to make them be the same length. And now, then let's multiply these together. A of x times b of x. And let me just write a of x down here, and then b of x. Now, if we were multiplying this out, we would take the first one here and multiply it times everything, and then the second one times everything, all the way up to the last one times everything, using the distributive property.
So do you get 6 dots instead of 3?
9 maybe. So we have a0 times b0, b1x up to bn x to the n, plus a1 times it all.
Why do you need the A1?
Oh, I need an x times it. I forgot the x.
So next would be A2.
The next would be a2, but I'm going to skip it and go straight to the end. an x to the n times, yeah. I don't want to write them all out.
Would you mind? I wonder if someone's actually going to do that.
I don't know. And then you distribute the a0 through everything, So you're distributing twice on this, so we get an A0, B0, plus you get, for the x term, you can have an A0, B1, x.
You distributing the first one, you said?
Yeah, I'm distributing the first one through. And I'm actually going to write things together in groups of x. You'll see in a minute. So we have A0, B sub n, x to the n. Now distribute the second one through, A1x through. And so that's going to be A1, B0x, and that's our x term, right? And then we're going to have an A1, B1 x squared. I want some space here. And then we'll have an A1, Bn minus 1 x to the n plus an A1, Bn x to the n plus 1. Does that make sense? So if we continue in this pattern, the next one coming down, if I actually was doing the A2 has an x squared on it, so you'd have an A2 B0 x squared. You guys see that? And then you have an A2 B1 x cubed, and so forth. Continuing down, let me go ahead and write that one under the x squared because we're going to need this pattern. We're going to have an A2 B0 x squared. Yeah, all the way out to, this would be an A2 Bn minus 1 x to the n plus 1 plus an A2 Bn x to the n plus 2. Not that the n plus 2 really fits on the screen, but that's what's right there. So you see, you kind of have this diagonal pattern that's going through this when you line up the x's. You're going to keep on going until you get to the very last one down here. And this one starts with a n b0 x to the n, so that's going to line up with this column right here. So then this becomes plus a n b0 x to the n, and it goes all the way over to a n b sub n x to the 2n. You guys see that pattern? Now, when you're adding all of these together, combining our like terms, we have the a0, b0. That's our constant term out in front. It's the only one that's all by itself. What multiplies the x terms? A0, B1 plus A1, B0. That makes sense? What would multiply our x squared terms then? A1, B1. And is that all, or is there another one that's going to multiply the x squared? Notice I didn't put the x squared on the first one. We have an A0, B2 x squared. Does that make sense? On the first one, we have an A0, and then B2 goes with the x squared. Right there. From that, do you think we can see what would go with the x cubed terms? Notice something about this pattern here for the x squared terms. The sum of these numbers here is 2. The sum of the indexes is 2. So can we figure out what would go with the x cubed terms? Well, let's start with an A0. A0, B3 plus A1, B2 plus A2, B1, A3, B0. That makes sense? All the way up to the x to the 2n term. And what goes with the x to the 2n term? an and bn. So the coefficients for each of the terms the coefficients are going to be of, let me write them down, of x to the j is given by is the sum of, let me use x to the k because I want to use a j in the summation notation. J plus I equal to k of a sub j, b sub I. That's the coefficient of the x to the k term. Does that make sense? You notice that the book just kind of said it. That's where that's coming from. So, we have done part one. We use the distributive property. Oh, I can't write with the pen on this one. I actually have to type it.
You can do it, it'll just take a while.
Yeah. So this is on the scratch paper. We now understand how the multiplication works. So now we want to go and verify the associative law, the associative property for multiplication. We'll come back and get the associative property for addition in a minute. So the associative property for multiplication for our field A of x, we assume that A is a field. That's what we're doing in this chapter. Assume that A is a field, and we want to look at A of x. We need three polynomials, A of x, B of x, and C of x in our field over x. We have to look at the associative property. Associative property means we're moving the parentheses through. So let's consider this.
I'll do it.
So we're going to have A of x times B of x and C of x inside our parentheses. Yeah, we're going to actually show how to do that. Now, I'm going to actually take this. Let's go calculate our B of x times C of x. By our formula, if we do B of x times C of x, that's equal to something the book is just going to call some D of x, which is equal to D0 plus D1x plus, and we'll get our dots. Well, I can't see that far away. Our dots up to, we're going to call this D2n x to the 2n because we're going to assume that the degree of each of them, sorry, not the degree, but the number of terms is n for each of them, where we've added 0 terms as necessary, like we did in multiplying. So that's going to be that case right there, and we can define what each of those values is going to be. Bk is equal to the sum I plus j equals to k of a, I, b, j. C, I, yeah, b, I, and c, j. Yeah, I forgot which direction we were going first. Okay, so now let's plug that into this multiplication down here. That just becomes a of x times the d of x, right? But now apply your multiplication rule to a of x times d of x, and you get this is equal to some r of x, which we can call r0, r1x, plus all the way up to, what is the power for this r of x going to be? Yeah, r3 sub n x to the 3 sub n, because it's the third polynomial. D has 2 n's, and so we add the number of terms, the 2n plus the n for a gives us to the 3 n's. And now we have to write down the formula.
Is there a plus sign between R0 and R1?
Yes, there is. Just didn't get typed. And let's write down, what do I know about RW, say? This is equal to the sum, I don't know, S plus T equal to W Oh, no, that's supposed to be down here. Yeah, R plus T equal to W of A, S, and D, T. But then, what was dt equal to? Yeah, we're just going to plug that in. Oh, not quite the whole thing. But we're going to replace D by our definition for D up here. Yes.
Do we need to replace it with K's?
Yeah, we're going to actually get that replaced. Okay, but here we have T was what we had, and so the K then becomes our T here, right? Yep. Now, what happens when you have a constant outside times the sum? You can take it inside the sum. It's like a 2 or a 3. This is a number out here, so I can take it inside the sum.
Would it be wrong to be using K in both those, like above and right there?
No, you could probably use K as long as you use it the same.
Okay.
But I use them different so that I wouldn't confuse anyone. But you could use it the same. Now you have the summation of a summation. But I suppose we can keep our sums next to each other. It's just a summation of a summation. Now, help me out. Can I... We have two options. We can go back to the top and start working, or we can try and work backwards. Which way do you want to go? Because we have done A times B times C. Now we have to do A times B times C. Do you want to work this one backwards, or do you want to start at the top and come back to the middle? Start at the top and come back to the middle, okay?
But wouldn't that basically be the same as we did?
Yeah, it's just switching the order of how we do it.
So let's do it backwards. It's the same thing.
It'll get you the same thing.
Okay, do that.
Do what? I didn't hear what you said, so you're lucky. Okay, so you want to see it backwards. You can regroup inside here, right? Yes. So let's regroup inside. But regrouping inside this AS times BI, yeah, we have S plus I needs to be equal to J inside. I guess changing this over here might be a little more confusing than coming down from the top and seeing that it's the same thing.
Could you combine the summations by combining putting I plus J in for T where S plus T equals W on the little bottom part at the very bottom and get rid of one of the summations? For
Yeah, that's a good idea. Let's do that. You can do that. Good call. I was going to try and do that without doing that, but it'll make it much easier. You know that T is equal to I plus J, so we're going to take the I plus J over here and replace it for that T. And then we can get rid of that notation right there. Which makes this down here just a little bit easier. Allows me to change how we sum it. Oh, down
Do you
here.
not have a scroll function? Do you have that really back there?
I do, but my mouse is super sensitive, and so it'll scroll too far.
And did you say?
No, I did not. Let's do that. Remember that last time? Yes.
Especially with those displays.
Yes.
That's what I'm
And it's so easy to do that. You'd think I'd learn. I've done it more than once, and I've done it in front of class more than once. Okay, so then how do we reorder this? We have the S and the I and the J. we want to make this into two summations, so we want the J one, kind of, see how we have this split up here? We have the I and J inside, the one in parentheses is inside. So yeah, I'm just going to bring this down and split it back across. So here we have the S and the I, so we want I plus S right here. For the,
Should be S plus 2 be true?
yeah, we need to copy this down. Yes, we're going to change all of the notation there. Okay, so we have the I plus S plus I for the B part, and then the J comes out here. We have, is that the right one?
Should that be, T be changed in I?
Or should it be changed to?
Okay, we need a K floating around. Oh, this is a T, and that T goes over to here.
So it should be J plus T?
Yeah, J plus T, yep, that's right. We want J plus T equal to some W.
We need to switch this.
We got this backwards. Let's go back and compare it to this one up here. We have S plus T equals to W, and then the T is I plus J inside here. And so we want, no, I think that's right. Yeah. And then we split it up into the two notations, right? Equals. And now this one comes over to there. And that, I'm going to just put in parentheses. And then this is going to be over here, and we call this whole thing, I don't know, we called it R before.
But it's A and B now, so it shouldn't be.
Something different.
How about?
Q? What'd you say?
U.
Pick a non-Greek letter.
L.
L.
You did pick a non-Greek letter. Let's not pick that one either. Let's go with the L. So, and this is L sub T, right?
Yes.
Okay? So then, what is all of this equal to? This is equal to our A of X times B of X times our C of X, right?
Yes.
Notice that in the middle, we got to the same value. So we could say, well, that's where the RW. So we got to the same value right here in the middle, meets in the middle, therefore associativity for multiplication works. Do that. Okay. Now, what you guys are going to try and do is try and prove the commutative property of multiplication. You only have to multiply two of them together. Much shorter. So you're mimicking the same type of idea of multiplication. Do you want to see the proof, or do you want to see the scratch work on the screen? The proof doesn't all fit. Let me move some of this around so we can get more up here. For multiplication, that's not hard. Oh, that did not work. It likes to reorder all of these things for me. I don't know why it's so helpful. There we go. Now you can see a little bit more. You don't have to do that third one. You're not going to have two sums. You're only going to have one sum.
Can you spell a little bit?
Up or down? Do you want to see that stuff right there? Yeah, you don't need it. You just need A of x and B of x. And then you're gonna be using what we did kind of in our scratch work to see that they're the same. Okay, and I'm gonna wander around and look at outlines. Wait, do what? Yeah, you're doing it using the sums, but you're not gonna need two sums.
Yeah.
You only need one.
Okay.
Yes. Pause this now. What'd you say? Did I miss it?